In this discussion video, we will talk about finding where piecewise functions are differentiable. So I want to motivate that by first recalling the definition of a differentiable function. So we say that f is differentiable at x equals a if f prime of a exists. So f prime of a is the slope of the tangent line. And what this is saying is the slope of the tangent line is defined. So there's got to be a way to draw the tangent line for the slope to be defined. And moreover, whatever the tangent line looks like, it can't have an undefined slope. All right, so conceptually, a function f is not differentiable at x equals a if one of the following happens. So all of these scenarios will correspond to a situation where the slope of my tangent line is going to be not defined. So the first is if my function f is not continuous at x equals a. If it is not continuous at x equals a, or I could have said discontinuous. So to draw a picture of that, let me draw some axes. And I'll put a here, and maybe my curve does something like this, and I have a hole. And then I have a closed circle maybe down here, and it does something like this. So discontinuity, the issue there is, because it's discontinuous, I can't draw a tangent line. There is no tangent line. Because it's unclear if I should draw the tangent line somehow, at this left piece or at the right piece. I can't really draw a tangent line. And if I can't draw a tangent line, well, I can't even talk about the slope. The slope of the tangent line is definitely not defined. Okay, the next scenario where our function is not going to be differentiable is if f has a sharp corner, or a cusp. So a sharp corner is something that looks like sharp corner like that, maybe like a straight line segment, sharp corner. A cusp is if it's more like curving up to a tip point and then curving away like that. But they're very similar. So if you were to use these terms interchangeably, I wouldn't mind. Okay, so if f has a sharp corner or cusp at x equals a, and the scenario in both of these is that I can't draw a tangent line either. There is no tangent line. And I'll put another sad face. And to indicate why, in this first V shape, in terms of this point, it's sort of unclear. Well, do I use the slope of this part to draw the tangent line? Or do I use the slope of the other part to draw the tangent line? And because of that, there isn't a good consistent, let's draw the shape back in. There isn't a good consistent way for us to draw the tangent line, so the slope is not defined. All right, and the final situation where my function is not differentiable is if f has a vertical tangent line. Now let's write that better. F has a vertical tangent line at x equals a. So let's draw a picture of this one on some axes. So I'll draw some axes, and I'm going to make my function get completely vertical for a split second. Let's say it happens here, and then it continue onwards. And this x coordinate I'm going to call a. And let's draw in that tangent line. I made it get perfectly vertical just for a split second. So this is a tangent line. So we could have a graph that's like this, that gets momentarily vertical just for a split second. And the issue with that is with a vertical line, this has an undefined slope. So there is a tangent line here. It just does not have a defined slope. So our function is not differentiable at a. All right, so I'm going to do a practice problem now. This is from worksheet 6, problem number 6. It involves some piecewise functions. I mentioned in the title of the video we'd be doing stuff with piecewise functions, and we're ready for it now that we've done that review about differentiability at a point. So the question says, evaluate the derivative of each function, and for what values of x are the following functions differentiable? So I want to have you first try part A for 4 minutes. 4, 3, 2, 1, pause it and try it for 4 minutes on your own first. All right, so let's talk about these together, or part A first. So when I have a piecewise function and I want to take the derivative, I just take the derivative of each of the pieces. So for 9 halves x, that derivative is just going to be 9 halves, because the derivative of x is 1, and 9 halves is a constant that's multiplying it. So I'll get 9 halves times 1. Okay, and then if this is when x is less than 9, and for the bottom piece, x root x, this is x to the 3 over 2, if I simplify it. So if I use some power rule, I'll get 2/3 x to the 1/2 when I subtract 1 from the exponent. Okay, and the one thing that I have to be careful about is I can't write x is greater than or equal to 9. Right now, I have to just write greater than, because it's kind of like with continuous functions, with piecewise functions and checking for continuity, in that when a piecewise function changes from one piece to another piece, there's no guarantee that those pieces, first off, that those pieces meet at the same place. They might be discontinuous. And then even if they do meet at the same place, there's no guarantee that they kind of like meet in a smooth way. Maybe they'll meet in a sharp corner, or they'll meet in a cusp. Okay. So I know that may be a little bit confusing, but the key thing that I'm trying to say about this is I can't include 9, since our function may not be differentiable, which I'll abbreviate as diffable. It may not be differentiable at x equals 9 at that transition point from one piece to another piece. Okay, so the only point I need to worry about is x equals 9. So check if it's differentiable at x equals 9. Because if it is differentiable, I will get to put an equal sign here. All right. So to check if it's differentiable, we will first check for continuity. I'll first check for continuity, and if it is continuous there, then I'll check to see if it's smooth. So if it sort of has the same slope from both sides. Okay, so for continuity, what we need is the limit as x approaches 9 from the left of our function g of x to be equal to the limit as x approaches 9 from the right of g of x, and I need that to be equal to g of 9. So let's do these. Let's find the limit as x approaches 9 from the left of g of x. So we have the limit as x approaches 9 from the left. And on the left side of 9, that's the top piece. The x is less than 9. So I'm going to use 9 halves x. And now with this, I can plug in to get 9 halves times 9. And multiplying, we get 81 over 2. So nice. Let's do the limit from the right. The limit as x approaches 9 from the right of g of x equals the limit as x approaches 9 from the right. And on the right side of 9, x is going to be bigger than 9, so I use this bottom piece. I'm going to use x root x. And if we plug 9 into that, we get 9 times root 9, which is 9 times 3, and that's 27. So I don't even need, at this point, to figure out g of 9. These are already different. So since these are different, f is discontinuous. And if it's discontinuous, and thus it's not differentiable, it is not differentiable at x equals 9. So the answer for what values of x is this function differentiable? The only place I had to sort of worry about was at 9. And I see that now it's not differentiable at 9. So the answer here is that f is differentiable f is differentiable at all reals except x equals 9, and that is our answer. So if we return to the derivative, because it's not differentiable at x equals 9, I don't get to put an equal sign and say, oh, this is greater than or equal to. I have to leave it like this. So this is going to be my derivative up here. Okay, let's move on to, actually before we do part B, I want to have you try it now. So I know part A was likely kind of tricky. I was kind of throwing you in without, having done an example like this. But now that we have, I want you to try part B. So 4, 3, 2, 1, pause it and try B for about 6 minutes. Alrighty, so hopefully you've done that. Hopefully paused it and tried part B for about 6 minutes. So similarly for part B, we only need to worry about x equals 9. Everywhere else, it's definitely going to be differentiable. Okay, so first, let's check continuity. And then if it's continuous, I'm going to make sure it's smooth there and check the slope from both sides. Okay, so for continuity, I want to leave this as an exercise for you because it's going to be really similar to what we did before. We're going to check the limit as x approaches 9 from the left of our function equals the limit as x approaches 9 from the right of our function equals g of 9 when you plug 9 into it. And in return of that, all three of these equal 27. So I want to leave that for you to check. Okay, so it is continuous. That doesn't necessarily guarantee it's differentiable because I could have a situation where that's continuous, but it's not differentiable because it's not smooth there. I need the slopes from both sides to sort of be the same finite number. Okay, so we are now going to check the slopes from both sides. From both sides. Okay, so let's take the derivative of our piecewise function. So if I look at the top piece, the derivative of 9 halves x is 9 halves. Is 9 halves. And then the derivative of that, what was it, minus 27 over 2 is going to be 0 because that's a constant. So we'll get this if x is less than 9. And for the other piece, we've already done that derivative before. It was 2/3 x to the 1/2. And we're going to get that's the case if x is greater than 9. I don't get to put an equal sign here just yet for the same reason. So I can't include, oops, let's put the L, can't include 9 since it may not be differentiable, all right, diffable at x equals 9. I haven't checked fully that it is. Okay, so I need to check the slopes from both sides, and that involves taking the limit as x approaches 9 from the left of the derivative of g prime. Okay, so we'll have the limit as x approaches 9 from the left of, so if I'm on the left side of 9, I'm going to use the top piece, the 9 halves. And with that, there's nothing to plug into. So when I do plug in, I just get 9 halves. Okay, now let's do the limit as x approaches 9 from the right of our derivative. Okay, so this is going to be the limit as x approaches 9 from the right. And if I'm on the right side of 9, I'm going to use this bottom piece, 2/3 x to the 1/2. X to the 1/2 is the square root of x. And if I plug into this, I'll get 2/3 times root 9. And root 9 is 3. You know what? I'm realizing I miswrote this. This shouldn't be 2/3. I believe it should be 3 halves. Let me just double check. Was it 3 halves above? Oh, you know what? Even before I did this incorrectly. It's good I caught this. All right, this shouldn't have been a 2/3 because when I bring this power down, I get a 3 halves. Okay, so good we caught that. All right. So that should have been a 3 halves. Okay, so this is 3 halves x to the 1/2, so I should have a 3/2 here. Okay, so 3/2 times 3, that is 9/2. So what this is saying is, when you take the limit from the left, it's sort of saying like, okay, as you approach 9 from the left-hand side, the slope is going to be 9/2. So whatever happens, as you get close to 9 from the left, the slope is 9/2, something positive. And the limit from the right is saying, okay, as you approach 9 from the right-hand side, the slope is the same. And we already know that it's continuous at 9. That's the part I want to use check. So they are going to meet. But now I know that they meet sort of with the same slope. So it is smooth there. All right, so thus, G is smooth at x equals 9. So since it's also continuous, let me just write continuous at x equals 9, this means that G is differentiable at x equals 9. So we're ready for our conclusion. So we can say where it's differentiable overall, G, my function, is differentiable. The only place we needed to worry about was 9, and now we know it is differentiable at 9. So it is differentiable for all x. And the other part of this question was writing that derivative. So our derivative was that piecewise function. And what we had was, let's see, we had 9/2 for the top piece. That's if x was less than 9. And the bottom piece was a 3/2, not 2/3, 3/2 x to the 1/2. And that was if x was greater than 9. And now we've checked that it is differentiable at 9. So I do get to put an equal sign here. It technically doesn't matter if I put it on the bottom piece or the top piece, because I know that they perfectly sort of meet. All right, I'm just putting it on the bottom piece because that's where it was in the original piecewise function. And that is my derivative.